session. This is the last session before you have valedictory. This session will be chaired by Professor Dr. Rajiv De of Jadavpur University. Rajiv is here. Rajiv. We can. Then there are 3 presentations from domestic and 1 overseas. Vibhor Sharma is the director, Anand Coats. Then Sarosh Singh, he is a professor in Adamas. Shankar Chaudhary is the CEO at Mastco. And Sujit Sengupta is the founder at Mira Canada. He will be online. Yes, Rajiv is here. There are 4 presentations, 1 from overseas. Over to Rajiv for conducting this. And I request that presenters to please be on the dais. Is Vibhor here? Vibhor? Yeah. Vibhor, Sarosh, Professor Rajiv De, and actually Vibhor after the we can do it. Vibhor. We can. Hello. Sujit is not there, of course. Yeah. To you, Rajiv.
Good afternoon. Basically, this is the last session of this particular seminar, and after lunch, definitely it will be very tough to conduct a session. So, without delay, so I request Mr. Vibhor Sharma to give his lecture in front of you. Mr. Vibhor Sharma is a director at Anand Coats Private Limited, focusing on innovation in specialty chemicals and decarbonization solutions. His work spans steel additives, binders, functional polymers, corrosion protection, and coke oven process optimization, including coal blends and moisture management. I personally know him. He is a very enthusiastic guy who has a keen interest in developing technology, and obviously I personally came to know a lot of things regarding the present market situation, regarding the newer materials from him. So I am very much eager to hear from him. So without delay again, so I request Vibhor to start. And Mr. Shane, what is the time? Time duration? Yeah, I know. So your time is between 10 to 15 minutes. So I think you should keep yourself within the time. Okay. Thank you.
So very good afternoon to everyone, and a big thanks to Rajiv sir for the introduction. So speakers on the dais and off the dais, we'll straight away get to the point. As sir mentioned in my introduction, we are working on specialty chemical innovations. Now here, the subject which we are speaking today is very, very relevant to the ferroalloys industry, where we are seeking a cost-effective and sustainable value creation. I'll straight away get to the point. Our solutions at Anand Coats are science-backed solutions, commercially proven. Now we are a DPIIT recognized startup. We operate at the intersection of specialty chemistry, material science, and industrial process optimization. Now the core principle which guides all our innovations is to reduce operating cost and lower carbon footprint at the same time. Normally, whenever we talk of carbon footprint reduction and cost, they tend to go inversely proportional to each other. But we work with an objective that if our initiative brings commercial benefits to the customers, it will be immediately adopted. And that is why we call it as net negative cost decarbonization. Sectors, we serve iron and steel, ferroalloys, and DRI sectors. Group experience and pedigree, our group company, Shrichem Resins, has been into binder manufacturing for the last 37 years. For the ferroalloys, we have developed ULP binders with a track record, and we have also been recognized as one of the Tata Steel Innovista finalists. Now, when we talk of innovations, we are not only in the lab, we are field proven, we are in the plant. Now, active pilots running at major integrated steel producers across 4 distinct initiatives, demonstrating value in use, where the product outweighs, brings benefit which are more than the cost, input costs which are being incurred. So what are the initiatives which we are right now piloting? First is a PCI coal additive. This additive is applicable for the blast furnace area, where we are delivering a coke rate saving of 2 kg per ton of hot metal by using our additive. This additive goes in a powder form along with the PCI coal which is being injected in the blast furnace, and the impact is a saving of 2 kg of coke rate. Now cost wise, our additive cost is only up to say around 17 to 18 rupees per ton of hot metal. The impact of 2 kg per ton saving in coke rate is alone more than that. So it's a VIU positive. Similarly, we are working on DRI coal. DRI coal right now the pilot is going in a 500 ton per day kiln. We have the target of reducing the coal specific consumption. Again a VIU positive case study. Pilot has already commenced mid of January. We are almost 2.5 months into the pilot. And once the trial is completed after the 6-month window, we'll be discussing scale up operations with the customer. Agglomeration solutions, industrial fines and byproducts. Now we, in addition to being only in binders, are also evaluating BOO based models with few of our customers, where we will supply the binder, we will do the agglomeration and return the product, agglomerated product to the customer. So those BOO models are also being explored with a few of the key strategic partners. Iron recovery from waste. Now this is very interesting. We heard in the previous presentation regarding the potential of hydrogen, the potential of directly reducing, getting value deriving metal from the ores. So we have filed a patent which basically specializes in recovery of iron from iron rich wastes like mill scale, red mud and iron ore slimes in an induction furnace atmosphere. So induction furnace is normally a pure melting furnace. There is no smelting reaction which is happening. So that is where the technology is. We have a precursor which we call as SACA, super activated carbonaceous additive, which is the main technological innovation which enables this process. This process is at a decent maturity level. We are already at TRL 5. We have done extensive lab scale trials, and next month we expect to move to TRL level 6, which will be a plant scale trial, approximately 1,000 metric ton full scale campaign in a plant. Now coming to the ferroalloys problem statement, the molasses problem. Cost wise, it's one of the lowest cost binders accepted across the industry, but sometimes the consequences can be high. It has been the default option, but then let's have a look at what are the potential shortcomings. One is high phosphorus, elevated phosphorus content in ferrochrome, a direct penalty on the quality. Long drying time, 4 to 5 days is the drying time required before the briquettes can become usable. Specification variability. Now it's a waste product of the sugar industry. There's no particular specification. So there's a lot of variability in the feed, which again impacts your plant operating parameters. Moisture sensitivity. It's mandatory to have a pre-drying step where the chrome ore needs to be brought down to a particular moisture level. Otherwise, the bond which is formed, the lime succinate bond, that will degrade. The quality of that bond will come down, and that affects the briquette strength directly. Again, very important, furnace disintegration. The high temperature stability is very, very important. How closely it is being monitored by different industries is again a big question, but then the briquettes don't have, the lime molasses briquette don't have a stability beyond 500 degrees. Supply and compliance risk. Again, this is beyond cost. There are very strict policy guidelines, excise and other parameters which are there for the molasses. In addition to that, there's another challenge, ethanol related diversion. And with the Middle East war, this situation is aggravated. While lime alone cannot fix molasses, the chemistry everyone knows here, everyone here out here knows, people are expert, but I'll get down to why the chemistry performs below expectation in practice. So 3 key points. Variable sucrose content. The content, it's not a product, it's a byproduct or waste product. So there's a lot of variability in the sucrose content which affects the strength from batch to batch and from plant to plant. The moisture in the chrome ore dilutes the active sucrose. That dilution again leads to a loss of strength. Even with optimal lime addition, you require minimum 5 days of curing time. Now what we are offering? We are offering a new generation binder based on nanochemistry, which we are calling as N-bond. What it is? It's a manufactured hybrid liquid system with nanotechnology enabled formulation. Now it is designed as a direct standalone substitute of molasses. So we are targeting 1-to-1 replacement of molasses. We want to eliminate molasses from the system. What it solves? Now this is very critical because as I mentioned, moisture degrades the lime sucranate bond. Our binder is not dependent on that. So we can handle up to 3% moisture in the system. So where the moisture level is within this tolerance, you can eliminate the pre-drying step. That will again bring you energy and cost savings. What it enables? In addition to the required strength, it also brings superior thermal stability in the critical zone of 500 to 700. That basically ensures that your overall reduction in yield which is being obtained will be at the optimum level as per your design chemistry. There is also a possibility, because it's a cold bonded process, compatible and gives good strength, so you can design composite briquettes containing carbon fines. That is again a very, very new subject which can dynamically alter how a SAF reactivity or the furnace behavior operates and can bring potential cost savings also. We are also working on manganese ore. Agglomeration problem statement related to manganese are very rare and few, but we are working on that and it is also showing encouraging results on that. From lab to plant, from innovation to recognition. So the predecessor which we had was in our portfolio was the ULP binder, developed by a group company, Shrikam Resins Limited. 100% molasses. Initially we started plant trials. We got support from few of the innovation-driven ferroalloys manufacturers also. One of them being in West Bengal, who initiated this project. We started with 50% molasses replacement and finally reached up to 100%. We have already supplied 3,000 plus tons of this material commercially. We were also shortlisted as a recognition in Tata Steel Innovista as a finalist in the most innovative vendor category just the preceding year. Now the current generation, the product is called N-bond. It addresses the cost competitiveness gap. Now why our ULP binder could not scale up, one of the primary reasons was that it was a resin based binder, and because of that the polymer cost was very high. So it was priced significantly higher than the molasses. Now this N-bond reduces the cost parity. So it's almost, you can say, in the range of molasses, slightly higher. So that cost competitiveness, we believe, will enable wide scale industry adoption. Controlled plant scale trials are already underway. We are already in discussion with a couple of industry partners for doing bulk scale trials. And it also accommodates composite briquettes. Now coming to the next product, which we are believe has a lot of potential in the ferroalloys industry, is reactive anthracite. So we all have used anthracite to a certain extent in our SAFs. We have been working on a lot of reactivity related chemicals and additives for the coal and coke requirements. So by virtue of that knowledge, we have already, for the induction furnace requirement, we have already developed a reactive anthracite which is having a significantly higher reactivity index as compared to the traditional anthracite. This optimized, basically what it does, it ensures that there is a better carbon pickup, the furnace operations are efficient. We believe this anthracite also has a potential in the ferroalloys industry. So specification consistency will be maintained by us. What we request from the ferroalloys manufacturers is discussions on how the trials can be taken. We have already deployed it in induction furnace, where we have proven that it is performing better than the traditional anthracite. And with that, we have expectation that the similar performance would be demonstrated. We have also done, beyond expectation, we have also done a few studies like TGA analysis, TGA MS analysis, to analyze what kind of gases are being generated at what temperature range. That gives us an idea that how the reactivity behavior of the anthracite is changing with our processing step. Now the bigger picture, sustainability that pays for itself. So our central theme is the most durable part to decarbonization is the one which makes commercial sense. So if commercial sense is there and decarbonization is achieved, we may not be able to achieve what CCUS is achieving, but then what is the largest capacity CCUS plant which we have in the world? So if we can give a commercially viable initiative to the plant which can help them decarbonize, we believe there can be very, very quick and widespread adoption. So products, again, reiterating and repeating, N-bond for the agglomeration problem statements, molasses substitute, reactive anthracite, we believe as a better reductant, more efficient reductant in the SAF, agglomeration and iron recovery. We have been working on a lot of problem statements related to waste, circular economy, and we welcome industry to have interactive, constructive discussions with us on these lines. So what we believe, with the closing remarks, the ferroalloys industry is at an inflection point. Molasses supply risk, reductant, quality variability, energy cost escalation, ESG driven product and quality standards which are kicking in. It is creating a strong and urgent pull for science-backed solutions. So Anand Coats is ready to partner with ferroalloys producers for getting measurable value in use today and a demonstrable lower carbon footprint tomorrow. So what we ask for? Discussion and trials. Thanks.
Thank you, Bivor. Yes, this is again indeed a very good, I think a newer technology, some newer technology he has given. So in his lecture, he has talked about the newer additives and he has talked about the disadvantages of molasses, especially in terms of phosphorus loss and the making of composite briquetting. And actually, though he has told that actually, though molasses is a low cost material, but a journey from the low cost to true cost needs to be calculated. So this is a very interesting thing. And lime cannot simply fix the molasses. So they have talked about a newer binder using nanotechnology, which I think they want to replace it. The molasses will be replaced by that particular binder. I think Dr. Onrin Bhattacharya, I don't know whether he is there or not. In your recital, he has talked about because our industrial waste from steel plant, we have done, one of my PhD students is doing this thing, but they have done it with molasses, and Onrin and his company has replaced molasses with a newer resin, something like that. So this is again in the same direction. They have also invented some newer thing with nanotechnology. And another thing is there, the second part, he has talked about the reactive anthracite, which will be used for ferroalloys in induction furnace especially. But my question is how it will be used in the submerged arc furnace. So whether if we want to use it in submerged arc furnace, whether the same type of productivity will be there or not. So this is one question I have for Bivor.
Sir, that's a very, very valid question which you have regarding the behavior of anthracite. Now, anthracite as a reductant has already been used to a certain extent by most of the ferroalloys manufacturers in their plants. It has a reaction kinetics. As per the TGA, we can see that around 1050 or 1100 degrees, it starts participating in the reactions. Now, what we are trying to do here is to ensure that the reactivity starts at a lower temperature. So when it starts at a lower temperature, then the anthracite starts participating in zones, melting or reaction zones other than where it has been traditionally participating. So what happens if your overall process, the journey from the ore to the metal or the ferroalloys, if that process can be accelerated, the reaction kinetics can be accelerated. Here the limiting, we try to identify the limiting factor in the reaction. So the limiting factor is anthracite. So if we can modify the reactivity behavior of anthracite, the overall reaction kinetics of the SAF can improve. And that has potential in both productivity and also in power.
Yeah, but my point is, normally in submerged electric arc furnace, we are using low ash metallurgical coke. So for coke, there is ash, there is fixed carbon, but there is no volatile matter. So here, if we use the anthracite coal, so there will be volatile matter. So how you are taking care of that volatile matter?
For furnaces, this product is recommended for furnaces who are already operating at 15 to 20% anthracite. So people who have a concern of VM and are not using, because of, there are a couple of manufacturers who because of VM concern may not be using anthracite. So VM is a very, very valid concern. That will again create the tendency of flame and other things. Now, because of VM concerns, those who are not using will not buy the product. People who are already using anthracite can use it in a more efficient way. That is the picture.
Okay, thank you, Vibhor. So, our next speaker is Dr. Saroj Singh. His topic is Beyond Critical Minerals, Ferroalloys, Global Economy.
Thank you, sir.
No, 1 minute. I have to introduce you. Yeah. Dr. Saroj Kant Singh holds an executive MBA from ISB Hyderabad and PhD management from ICFA University, Jharkhand. Dr. Singh holds postgraduate degree in management, economics, finance and engineering. His research interests include project strategy, reconstruction projects in war-ravaged nation, policy making in the energy sector. He has 20 plus publications in Scopus indexed and ABDC indexed journals. With 22 plus years of experience in project management, business consulting, merger and acquisition, debt restructuring, managing large-scale industrial project portfolios at project management and project director levels, and formulating business strategy, he brings the experience to the classroom. Prior to joining academia, he served as associate partner of a firm specialized in systems thinking approach to business transformation using syntegration. The revolutionary process uses co-creation workshops to bring consensus and policy making. Now he is assistant professor in Adams University. Thank you.
Thank you very much, sir. And I would like to thank Steel Tech and Mr. Pritesh Sen to give me this opportunity to present. Today, my presentation will argue that ferroalloys should be treated as critical intermediaries in the supply chain policy, not just as industrial inputs. The core idea is that alloys like ferromanganese, ferrosilicon, and ferrochromium sit between minerals and final manufacturing. So disruption in this will cause risks into the supply chain and steel making infrastructure, etc. The critical minerals debate usually is around lithium and rare earth minerals, but this leaves out a blind spot of that of ferroalloys. Ferroalloys matter because they essentially enable the steel making industry, and they are also underpinning economic competitiveness, even when they are not framed as strategic under policy framework. The literature that is there is centered around mining scarcity, upstream dependency, and much is talked or not talked about processing and conversion steps. This creates a research gap because intermediate products are often invisible in the value chain, and what happens midstream will have impacts in the strategic place where India is heading to. Our contribution is a IRI style import reliance index framework into midstream ferroalloy discussion. So this is a conceptual framework, how risk will travel through the supply chain. What it shows is global concentration creates import risk, and this import risk due to import reliance is then transmitted to the supply chain risk. That supply chain risk ultimately will impact industrial outcome. In practical terms, we are formulating an index which will combine HHI or the Herfindahl-Hirschman index, which is nothing but the suppliers' concentration in the marketplace, and other indices. So here is that framework which shows that IDR tells how much dependent India is on consumption from import. HHI shows whether suppliers are concentrated more or they are dispersed, and TER reflects trade exposure. So what is our takeaway from here? That this indicator looks manageable, and it's a combined index which will give relevant meaning to structural vulnerability in the supply chain. So what we did is some data analysis, and we took data from 10 years using production, import, export, apparent consumption, and top supplier shares. And then we saw that the HHI, wherever it has high values, is showing a vulnerability. The main result is that vulnerability is highest where import dependence and supplier concentration overlap. And when we think of the dependence on China, and if you want to decouple from China, this will be a great concern. So if you look at the market structure, we can break it into two parts. One is the bulk alloys, which are mainly supporting infrastructure and mass steel making, and which brings economic reliance. And the other is a strategic dimension. What that does in stainless steel, defense, and some very important sectors. So this brings competitiveness and national security together. Now, when we talk of global risk, the supply chain is very high, the risk is very high, and it is fragile, mainly because the dominance of China in ferrochrome production globally, and South Africa remains critical for chrome ore production and ferrochrome sourcing. The main concentration of this makes any disruption in mining, shipping, energy, or trade can quickly cascade into India's steel and manufacturing. The IRI shows that it's not a theoretical construct, but it's a measurable strategic index which needs to be considered for national security purpose. So now we move from diagnosis to ambition. So we are very ambitious for 2035 to scale up, be more reliant, and increase our import-export strength. This means that raising India's global share substantially and reducing import dependency to 20%, below 20%. And if we look at the state-wise comparison, we will see that Odisha stands as the raw material and industrial hub for ferroalloys, and other states contribute differently for energy, import, and resource base. And one of the speakers spoke about resource to reserve. That should also be considered here. And what is the policy implication here? We should not have a one-state model, but a coordinated multi-state strategy anchored by comparative advantage. So what is our position in the global space? So there's a plus side that we are strong, capable, and we have also exports. Ferroalloy production base is significant in India, and meaningful goal present is there. Odisha is a cluster where we have an advantage of concentration. The negative side is that input dependency on imports for manganese and chromium and high energy cost. And one of the speakers said 40 to 70% of production cost is in energy. These are the negative sides. Now, why ferroalloy is important in policy? So one of the things is that it is very critical nowadays to defense sector, where special grade steels, corrosion resistant steels are used in many defense products and manufacturing. And so ferroalloys do not simply give a volume support, it is very strategic to our growth. And therefore policy should pay attention to it. Apart from defense, there is also much use of ferroalloys in green energy, like wind turbine blades and some nano applications. So this is very crucial for us. Now, what is this policy gap? Despite the importance of this sector, no formal critical intermediary classification is there. Neither they are categorized under critical minerals. And therefore, policy attention should be given in this place. And although there is a lot of upstream mineral policy, we find that it is absent for ferroalloys. Institutional responsibilities are also fragmented across ministries like mines, steel, power, and a system-based framework should be formalized. So we give a 7-pillar policy framework. We are saying that ferroalloys must be formally classified as critical intermediary. India needs to secure raw material through partnership, especially South Africa and Gabon. Processing capacity should be expanded through Orissa-based hubs, where India clustering already is at an advantage, and many, a speaker informed that beneficiation in South India is there, so those should be coordinated. Dedicated power tariff and broad energy reforms are essential because energy cost shapes competition. Active participation of India and positioning it within the China One policy, export policy should be done. Decarbonization support and CBAM readiness must be built into the sector policy. So now let me bring out the central point of this presentation. Processing defines power. That is what we say. Ferroalloys are often invisible in policy discussion, yet they are hidden backbone of steel technology and defense manufacturing. The real strategic advantage is not in access to minerals, but to control over this intermediary processing stage, which converts raw material into industrial usable products. If India wants to be a true China One+1 manufacturing hub, it must move beyond mining and build integrated strategy around raw mineral, energy, trade, and processing, and where ferroalloy will play a very important part. Thank you very much for this time, and any questions?
Thank you, Dr. Singh. It is again a very interesting topic. He has talked about the global concentration, actually the utility of ferroalloys, its global concentration to import reliance, and he has talked about import reliance index, minerals, alloys production, trade supply, and there are some drawbacks of the ferroalloy sector, and there are some remedies. He has talked about that. And why this ferroalloy sector is going, is gaining importance, because he has talked that more and more ferroalloys are being used in the defense sector. Actually, this is when I was in Dastur in around from 96 to 2005, we used to do a lot of project finance assessment for ferroalloy plants. Then at 2003-2004, I can recall, Mr. Supriyo Dasgupta, then CMD, has written a paper. And now I see that paper, whatever he has written in 2004, has not changed substantially in 2026. He then talked about the drawbacks of the Indian ferroalloy sector. I used to take one class in 4th year on this particular subject, alloy steel production, then ferroalloys. And one particular class is for the problems and prospect of Indian ferroalloy industry. So there, the drawbacks are the dependency on the raw material, because the rich grade manganese ore, rich grade, chromium ore, rich grade, titanium ore, these are not available, especially manganese ore and chromium ore are not available in India. So they needs to be imported, like say in South Africa. So again, he has talked that we should have a good relation with South Africa, with Gabon, and a technical sort of connection should be there to take the minerals from those particular countries. Then obviously the shortage of low ash metallurgical coke. Yes, we don't have that coke. The coal has to be imported from Australia. Like Bihor has told that some replacement of that low ash metallurgical coke is necessary. He didn't highlight that point, but I think this is also a very important point. And obviously the power, if I say the cost percentage, around 70% of the total cost of ferroalloy production is basically the the energy cost. So that energy cost, and for that, normally we used to install a ferroalloy plant in a hilly region because there the hydroelectricities are cheaper. And you can see that in Bhutan, the Bhutan ferroalloy, BFAL and BCCL, a lot of different companies are there. And one of the owner of BFAL is one of my student also. He is in London now. So he has talked about that. Yes, sir, we have the power cost is very less there. And obviously, there at that point of time, Mr. Supriyo Dasgupta has written, ferroalloy sector is not a very constructed sector because the steel sector, we have a lobby, but no such that big lobby is there for the particular ferroalloy sector, and that is why the railway freight and other things are not same, it is higher. So Dr. Singh also has told that this sector is not being recognized as critical minerals, so there are some problems in the project economics. So this is it. A very good lecture by Dr. Singh. Only one point. He has differentiated the ferroalloys in two types. One is ferromanganese type and one is ferrochrome. But I say it will be better if I say there are two groups of ferroalloys. One is a tonnage grade like ferromanganese, ferrosilicon and ferrochrome. Because 75% of the total steel is being produced actually as mild steel, low carbon steel, and 10 to 15% for the high alloy steel. So there, the usage of ferromanganese, ferrosilicon as the scavenger units, for deoxidation or desulfurization is higher, as well as the ferrochrome as the chromium substitute, the chromium source for the stainless steel making. And the other part will be the specialty grade ferroalloys. They are like ferrotitanium, ferrovanadium, ferromolybdenum, niobium. So much ferroalloys are there. Other than, so I think this can be the classification. But otherwise, Dr. Singh has given a very good lecture. So thank you.
Thank you, sir. Thank you very much.
So the third speaker is Mr. Shankar Choudhury. Basically, I don't have his CV, but I know him more than his CV. I have worked in the Dastur for 9 years, and we were, in the most of that time, 7 years, we were actually sitting in the same floor. So, he has a very tremendous knowledge on project management, that I know, definitely. And here, Katsi Steel Tech, I have met in the last 3 or 4 Steel Tech conferences. He is managing director of CEO of Atmastco. So his topic is the concept of CCU to green hydrogen from exhaust gas of submerged arc furnace. Shankarda.
Thank you, Professor Rajiv Dey. Of course, Rajiv and we share the same floor, and I'm very happy to see that Rajiv is now preaching students and creating wealth for the country. So in turn, he is also owner of a mines, that is human skill. Thank you, Rajiv. Well, thank you to Steel Tech to give me this platform to speak on some very subject. Actually, I don't know that I wanted to weight this, my thinking, this is wild thinking basically, to share this idea to all of you and work on the same field. Actually, this photograph, we built this ferroalloys plant of 33 MVA for Facor, Vedanta Group. And again, we are now executing 2 numbers of 18 MVA plant for Tata Steel Jodha. So while, I was, and in both the projects are brownfield projects. That means one furnace is operating by the side of it, and we are building this, we have built this plant and we are building the other plant. So, while I visit the site, every time I thought, that lot of waste gas, I mean, chimneys flaring through that. Of course, these days, the particulate matters have come down, but still it is gas. So this gives me always a pain, that why such a huge lot of gas? Can't we utilize something out of it? So that has, triggered me to make some deep study, and probably I have spent around over 500 hours on this same thing, through different literatures, through different possibilities, through different economic scale, and we being an EPC contractor, so I wanted to jot down some numbers, so which I am going to present in front of you. So, it is basically being a metallurgical engineer, of course, these equations are always, they have enriched us in different form. So what I thought that, first of all, what this gas contain, useful things. So first of all, in a closed furnace, the CO percentage, it varies between 60 to 90%. But in open furnace, it is less than 20, even sometimes it is less than 10 also, because a lot of dilution takes place in semi-open type of furnaces. But there is a reaction, it is called water-gas shift reaction, in which the carbon monoxide reacts with water and it forms CO2 and additional hydrogen. This is called water-gas shift reaction, and there are reactors available, proven technology. I mean, it is not being reinvented, because I worked in gas-based sponge iron plant where I was introduced with the reformer, where the natural gas is getting reformed and finally, methane is broken and then hydrogen used to be used in that. So based on that also, this water-gas shift reactor is also a type of reformer where, carbon monoxide reacts with the steam to give you CO2 and H2. So there are different efficiencies available at different stages. These are there. We can always talk to that. But let us go to the fundamental part of it. In semi-open type furnaces, basically it is not techno-economically viable because of the reason, there's a dilution effect, more nitrogen, larger compressors and pipe reactors, and then PSA inefficiency, lower hydrogen partial pressure and lower recovery, that is 50 to 60%, and the capex inflation, that is equipment size on total gas, not on CO. And energy penalty, more power per unit of hydrogen. So as a thumb rule, each 10% drop in carbon, reduces the economic attractiveness by 20 to 25%. And in a 9 MVA SAF, closed SAF, which can generate around 7 to 8 megawatt equivalent hydrogen energy. But a semi-closed furnace can be converted into near-closed furnace. My friend, Mr. Patnaik, is here from Arjikon. I discussed with him during the recess, and he said, yes, it can be very much done. And so these are some of the steps which we have to take. That is, electrodes sealing part of it is very critical, and the charging chute sealing and the furnace hood pressure control, which should be maintained slightly positive so that leakages are not there, and slip ring and packing seal improvement and burden permeability optimization. So with this, it is expected that a semi-closed furnace can be converted into a closed furnace, and about more or equal to 50% CO we can get in the waste gas. So with that concept in mind, basically the process flow will be like this. There's the gas collection from SAF hood. It is simple, not a very difficult task. We are already doing it. Then dust removal. Here basically some larger particle, because it should be absolutely a dust-free gas, almost a dust-free gas. So the larger particles will separate it through cyclone. It is a standard equipment. Then forced draft cooler, and then back filter. After that, basically this gas also have tar and other gases, like small amount of methane and other things. So therefore we need a gas cooling and scrubbing system. So this can be a, gas cooling and scrubbing is not a very rocket science, available standard equipment, no problem. Then water gas shift reaction, CO to H2, this is also a reactor which is available and it is practiced in market. It is a proven equipment. And the PSA purification of to 99.9% hydrogen, yes, it is there. This is also a standard technology, and we have equipment for that, and supplier also. And finally, compression and storage. So if you go through this process flow, all equipments are proven. They are there. But you need an integrator like us, an EPC contractor, basically. So we have to integrate this process into a whole project. That is our responsibility, and that we'll have to do. But one thing is here, while you approach to any investor, he'll first ask, "Kahan chal raha hai?" Bhai, chal to nahi raha hai, but ho sakta hai. So ye support करने के लिए हम लोग को we need some forward thinking people, at least कुछ भी एक तो फर्नेस से इसको स्टार्ट अगर करते हैं, ठीक है, उसका जो इन्वेस्टमेंट होगा उसका लिए पैसा भी मिल जाएगा मार्केट से, बाजार से, कहीं से भी. But somebody should encourage this startup thinking, which is very much absent in India, barring few companies. Most of the companies, and that is the reason the Atmanirbhar Bharat आज सक्सेसफुल नहीं हो रहा है. बिकॉज किसको देंगे हम? कुछ भी काम अगर आत्मनिर्भर भारत में हम करेंगे वो तो फर्स्ट टाइम करेंगे, isn't it? So but how? So some entrepreneur with modern outlook, forward thinking outlook, and of course some national feeling should come forward where we can get together and develop this whole system. In capacity and output, what I could, it's a pessimistic this thing I have done. The green hydrogen can be 4.85 TPD, can be produced from a 9 MVA furnace, whatever carbon monoxide is there. This is for my closed furnace, of course. Annual production is 1600 TPA. But a retrofitted semi-closed, I have slightly derated it, so it can do around 3.2 TPD with an annual output of around 1050 TPA. So EPC perspective in this process integration is the end-to-end process integration. So I have divided into two phases. Phase one, the conversion of waste gas to hydrogen. So gas and then cleaning, conversion, hydrogen separation, and compression and storage. Value maximization of residual streams, that is the phase two, because from PSA, the tail gas will be containing the entire CO2 amount, which water gas shift equation have shown that the product will be H2 and CO2. So this CO2 can be captured. So there are a lot of process for CO2 capturing. It is not, today it is totally proven. And last but not the least is the monetization of, monetization through carbon credit. So you can also, once CO2 you are removing from this thing and you are capturing CCU thing, so the carbon credit can also be availed. And then layout and operability excellence is the optimal plant layout, ensuring seamless continuous SAF operation, because it will be a greenfield, brownfield project. So that needs to be assured and designed for reliability, scalability, and ease of maintenance. EPC design consideration, this conversion of waste gas to hydrogen for closed and retrofitted SAF. This is high dust load handling. This is cyclone and backfilter. That system will take care of it. Then we need corrosion resistant materials in scrubber and WGS water gas shift reactor, PSA optimization and recovery of purity, green hydrogen storage facilities, and modular skid-based design for faster execution. In phase 2, it is shifted gas to CO2 capture, to CO2 utilization and storage. Tail gas to fuels, steam or power. I mean, tail gas can have 5 megawatt equivalent of hydrogen energy. PSA tail gas contains CO, H2, CH4, that is of low purity, can be reused in furnace fuel or boiler fuel. Option, recycle it to Samaj arc furnace or use it for WHRB. Carbon credit monetization, CO2 reduction via waste gas utilization. Potential reduction is around 42,000 TPA CO2 indicative. This is, of course. And then carbon price, I have considered around 400 to 1,200 per ton. This is voluntary market, and potential revenue will be 1.6 to 5 crores per year. Additional ESG investor, of course, attractiveness is there. ESG impact, it is utilize waste gas, reduces CO2 emissions, and support green hydrogen transition. This is the final outcome of my brainstorming, and this I want to discuss with everybody anytime, not in this seminar, but this is my findings. The CapEx, I have given a breakup for phase 1 and phase 2. The total investment will be to the tune of 50 to 60 crores. And but you see this revenue pattern of it. With 30% recovery of CO2, you will be, your revenue will be almost 42 crores. And with 50% CO2 recovery, it will be around 58, 59 crores. And with 70%, it is 75 crores. The astronomical figure. I first could not grasp myself also. 2 months I worked on this. And then I'm finding that through whatever route I'm going, I'm leading to these numbers. And the operating cost, of course, around 13 to 14 crores per annum. So the projected EBITDA is 30 crore in the very first 30% stage, and 46 crores in the 50% stage, and 62 crores in the final 70% recovery of CO2 stage. This is, something which I don't know. We are not thinking of it, we have not thought of it, but I found it is possible. Only we have to come with a pilot project where we can prove these figures, and it is possible. As an engineer, as a metallurgist, and as EPC integrator, I have total confidence on converting this thought into reality, and it is possible. Thank you very much.
Thank you, Mr. Chaudhuri. So this is Shankar Chaudhuri, whom I knew from a long before. Basically, his lecture actually gives me an idea how an ordinary thing, a very ordinary process, can be made extraordinary only by a mind change. So, yes, really, this is really extraordinary to me now. So basically, we all know that from a submerged electric arc furnace where the ferroalloys are being produced, so a lot of waste gases are generated. And only thing, we have to collect the gas, and a very ordinary process of dust removal using a scrubber or a venturi washer like that. Then gas cooling and scrubbing, yes. Water gas shift reaction, CO plus H2O equal to CO2 plus H2. Perhaps this reaction we are studying from class 8, class 9. But really he has thought about that. So he has shifted that CO to CO2 and H2. And in today's perspective, in today's world, sustainability is the real buzzword in our technology. And if we want to make steel through a green technology, we want hydrogen. And the cost of hydrogen is very high. We all know. So around, in Indian rupees, 280 rupees per kg. So it is very high. But if we just convert this CO through a water gas reaction to H2, so we will get a 99% pure hydrogen along with CO2. So yes, it will increase the carbon footprint. So he has just given an idea of CCUS, carbon capture, utilization, storage. So there are proven technologies by which we can capture the CO2, and maybe using some brine water or something like that, we can make calcium carbonate and utilize that calcium carbonate, or we can put it, the storage in a waste iron, oil and gas field. So though it is a costly process, but if we can do that, again, that money can be come back through a carbon credit. This is really very interesting. So in every way, we are gaining money as well as we make our environment cleaner. So thank you, Mr. Chaudhary. It is only a process of integration. So I request everybody to think about that. And yes, if a pilot plant can be made, it is really becomes beneficial for this particular industry. Thank you. Our last speaker of this session is Mr. Sujit Sengupta. He is P Engineering, is an electrical engineer and senior transit safety engineer with over 19 years of experience in critical electrical infrastructure, hydrogen energy systems, and rail transit safety across North America. His expertise spans high voltage electrical systems, transformer stations, power distribution networks, and electrification. Currently with Soteria Company, he leads safety and security certification, hazard analysis, and systems engineering for major transit projects, including the Los Angeles Automated People Mover, the Edmonton Valley Line LRT, and the San Bernardino County Zero Emission Multiple Unit Hydrogen Train Project. His work focuses on ensuring electrical system reliability, code compliance, and safe integration of advanced energy systems such as hydrogen fueling and battery charging infrastructure. Earlier in his career, he held senior engineering and safety leadership roles with Vale Canada, General Hydrogen Corporation, Praxair, and Air Liquide, where he worked on the design, commissioning, and operation of hydrogen plants, cryogenic systems, and mission-critical industrial power infrastructure. Mr. Sengupta holds master's degree in technology management and cryogenic engineering from the Indian Institute of Technology and a bachelor's degree in electrical engineering, and he is a registered professional engineer in Ontario, Canada. So I think he is there in screen. So I request Mr. Sengupta to start his lecture.
Hello, good evening and good morning. Can you hear me?
Yeah, this is audible.
Yeah. So good to see you, and all the discussion about renewable energy, sustainability, green steel, training, and all the stuff. So my presentation today and discussion today will be a good segue to what the previous presenter spent about green hydrogen. I am trying to set up a proposal and develop a proposal for implementation in India about hydrogen, green hydrogen, and its use in the ferrochrome, chrome and manganese production. And what I'm trying to do is similar to the concept of the previous presenter, have hydrogen usage in pre-reduction when you produce the ferrochrome and manganese. But I also have a lot of background in working in India before I moved to Europe and North America in my work. I worked in Tata Steel, so I have a very big, good background in steel industry. And then I worked in the various industrial gases, so I have a good background in CO2 capture, as Mr. Chaudhary was saying, CO2 capture, CO2 production, liquefaction, and then of course hydrogen. I was responsible for erection of the world's largest hydrogen plant in Bécancour in Quebec. So this gives me a good idea of where we stand. So I will start the presentation, and I'll try to answer all the questions that come up. It is a great pleasure to speak to you today. So I'll just share my presentation. Just give me a minute. Share. So, and then I will go to my presentation and go to slideshow from beginning. So, can you see my slide?
Yeah.
Hello.
This is clear. Yeah,
you can
this
see
is
my
clear.
slide.
Yeah,
thank you.
This is clear.
So basically what I want to discuss is hydrogen and its utilization in ferrochrome and manganese production. So it is not just only production of hydrogen, it is the use of hydrogen in a pre-feed stage in a rotary furnace, and then feeding it into the SAF submerged electric arc furnace and the DC smelting, all these things we talked about today. And the thing about hydrogen is that it can be reutilized. It can give you the benefits in terms of carbon border adjustments, green steel, and carbon intensity reduction. So it can be used. And the green hydrogen, it was a good concept that was introduced in the previous picture. The problem with green hydrogen is the purity specifications are very stringent for its use in fuel cells that I work with and electronic manufacturing. So it will be a good idea to use the hydrogen, green hydrogen with carbon capture, and use it in the process itself. So that's what I am trying to suggest and propose. So it is what I came through my research and my work is that it is the use of a hybrid pathway using a rotary furnace for hydrogen pre-reduction is a credible, de-risked thing that we can do. And then it is the best thing that we can do today to reduce the hydrogen footprint, the carbon footprint of the ferrochrome and steel industry. Next. So what it is a decarbonization of the ferroalloy production using hydrogen, focus on ferrochrome and manganese. These are easier to do. And then use a hybrid rotary furnace with the submerged electric arc furnace route in the near term. This is a deployable thing, as my esteemed previous presenter was saying, and we can really do it. So I intend to work with research institutions in India to develop this from pilot to commercial scales. So basically it is a technical fit, as we were saying, that we can do hydrogen pre-reduction. It could be a hybrid route which could be implemented in a brownfield site which already has ferrochrome and ferromanganese production. It has a commercial fit because it gives you access to the carbon credits and the cross-border carbon management and green steel specifications. And it is an execution fit also because it can be done with low risk systems compared to other systems. So what is this? We have the ore prep, we have the pelletizing and briquetting, then we introduce this rotary furnace, then we do a hot inner transfer to the SAF and DC smelter furnace. So thinking aloud, hydrogen can be pre-reduced, so it can reduce the energy consumption in the SAF or the DC smelter, and then the recycling, and then if we introduce a carbon capture step, then the hydrogen itself and the CO itself could be fed back to the rotary furnace. So this is a unique scheme that I have proposed, and if we do it, it could be like one of the few in the world that will have this capability. So what I'm trying to suggest is we have the feed, we put it into the rotating furnace in a counter flow way. The hydrogen flows in the opposite way, and we pre-reduce the ore before we feed into the furnaces. So the industrial context here is steel decarbonization is accelerating. Ferroalloys are a major hidden emission source, and then we have the carbon border adjustments and the ECG, which is driving the change. So as we talked about, conventional SAF uses coke and coal, and it has high CO2 emissions, 2 to 3.5 tons per ton of alloy, and energy efficiency and inefficiency in carbon exposure are the problems. So we do the ore, the crushing, the pelletizing, put it into a rotary furnace with hydrogen pre-reduction, hot transfer to SAF, alloy, and slag separations. So the technical mechanisms are gas-solid reduction using hydrogen, ferrochrome partial reduction, and improved porosity and reactivity of the burden. The rotary furnace role here is continuous. We have selected rotary furnace for the simple reason it's a continuous processing affair. It has a good gas-solid contact, and it's a scalable and proven industrial technology. Then this is the whole feed PFD, which shows the electrolyzer, or it could be coke oven gas or gas purified from the hot gases of the furnace. And then it would have the rotary furnace would have a drying and a reduction step, and then the gas would be recycled. So the temperature zone that it would operate it would be 600 to 1000 degrees centigrade. We would maintain the high ratio, maintain the proper ratio, equilibrium of hydrogen to H2O. The pressure of the furnace will be slightly positive to prevent air ingress. The resident time would be around 30 to 120 minutes. And then the instrumentation, of course, this will require a high level of instrumentation in terms of temperature, flow, gas analysis, and safety systems like the purge, the flare, and the leak detection and alerting. So the solution overview that we are trying to propose and design is a hydrogen pre-reduction in a rotary furnace, reduce carbon usage in the SAF. This is a very important thing that will happen. The carbon coal use will be less, or gas use will be less, and we will have a closed loop hydrogen recycle system. So the chemistry here again is the reduction of manganese and chromium ores, partial reduction, and water removal. So the executive insight is that the project economics, as suggested, will be driven by energy cost and hydrogen and electricity costs. And for the ferrochrome and manganese industry, this is the viable entry route. So electricity will dominate the energy use. Hydrogen production is energy significant, and the total megawatt of power that will consume is 3 to 6 megawatt per ton of alloy steel. So what we are proposing, we'll develop a pilot, 1 to 5 kiloton per hour, which will then flow into a demo and a commercial production. So we are trying to work on a pilot, develop an ecosystem which we can develop a pilot, and then we'll move to a demo if we can, and then of course it will be open for all the steel producers, and it is a good thing that we are interacting today to commercialize it. So the capex breakdown is electrolyzer. If we do green hydrogen from electrolyzer, this is one way. The other way is coke oven gas, hydrogen production, or using the off gas from the arc furnace to get hydrogen and recycle it into the rotary furnace. So then these are the systems that can be used for hydrogen. The cost of the capital cost of the furnace would be 20-25%. Rotary furnace would be around 20%, the rest would be the infrastructure balance. OPEX breaks down, electricity would be 40-60%, hydrogen 20-40%, ore and consumables will be the remainder. So we did some calculations, and this is what we came up with in terms of the economics, and then so we would try to achieve a hydrogen recycle efficiency of 85% and a plant availability of 92%. So this is an OPEX breakdown. So hydrogen purchase, of course, or hydrogen repurposing from the flue gases would be a cost. So the rest of the costs are equivalent. And then the revenues, we looked at the revenues that you will get. It's a cash positive, good revenue system. And then the cost waterfall we developed, the revenue, so the main is electricity, hydrogen, and then other OPEX, and we would have a good positive EBITDA. And the OPEX cost, which aligns with the previous presentation, the OPEX cost maximum is electricity, next is hydrogen, and then the ore and consumables. So this is an important side where we have checked the IRR, and it all depends upon the price of hydrogen that we use. So between $3 to $4.5 a kg, this is in American dollars, this would be a viable project. So the key financial insight is the electricity is the dominant cost, so reduce the electricity cost. Hydrogen is the second largest driver, so reduce the hydrogen cost of production, and explore innovative avenues and ways of generating hydrogen and reusing it, like the off-gas hydrogen production, the coke oven hydrogen, gas hydrogen production, things like that. And the break-even is, the note is even strongly linked to hydrogen price. So financial sensitivity, hydrogen price, as I said, should be between $2 to $6 per kg, which is achievable by using either the off-gases, coke oven, or hydroelectric power. And electric power is a key for any ferrochrome production, manganese production. And so basically the project viability will depend on the energy cost. So the strategic positioning of such a project would be integration with hydrogen hubs. India is doing a lot of work in developing hydrogen hubs. So this project could be integrated with one of the hydrogen hubs. And it would be aligned to producing green steel, which is a focus of India and the world. So steel emits a lot of CO2 and pollution. And if we can reduce the emissions from a steel industry, it will certainly give us a good benefit in terms of the certification of steel as low carbon steel. So it gives you an opportunity of premium product positioning. The risk, of course, hydrogen cost for volatility, we have to guard against it, the control of moisture and its challenges, and then the scale up and the operational stability. The mitigation strategy that I've developed for this project is the long-term power agreements that we could do, efficient gas recycle design, new innovative design of gas recycle, including carbon capture and hydrogen production, and then working with a research institution in India to validate the process and then scale it up to a demo style project. So here the last one of the last slides is that electricity is around 42%, hydrogen is 28%, ore feed 16%, consumables 6%, and maintenance. This would be the cost breakdown. Rotary furnace adds a dedicated pre-reduction process, and it can lower the coke use, reduce the downstream smelter burden, and reduce the power consumption. So sensitivities, as we talked about, is the electric price and the hydrogen price, and how we can recycle and reuse and produce hydrogen and its use, and how do you do the carbon capture for the CO2 that we emit. So basically the next steps that we are looking at, we are trying to develop a joint proposal for ferrochrome and manganese production, use a rotary furnace as a pre-feed integrator, and then launch a feed and a pilot test program. So we develop the work package together with our collaborators and then try to see, as mentioned before, like try to see whether there is a fit to really doing a commercial project. So that brings an end to my presentation. This is an aspirational presentation in terms of what we can do, how we can make the ferrochrome and the manganese production green and aid the steel production, aid the production of green steel, and how to make a world-class facility, establish a world-class facility in India. Thank you, and I'm open to any questions that you may have.
Thank you, Mr. Sengupta. This is really a thought-provoking lecture. You have talked about the decarbonization of ferroalloys using hydrogen, especially in ferromanganese and ferrochrome. But you have you have talked about role of rotary furnace. This is a newer thing. Conceptual feed process flow diagram, temperature, pressure, residence time, gas analysis, etc. are very important factors. You have talked about hydrogen pre-reduction in rotary furnace, and so the net gas use will be less. You have talked about project scale, pilot plant, its capex and opex breakup, a good EBITDA, and a curve between internal rate of return versus hydrogen price. And yes, the cost of hydrogen and cost of electrical energy is most sensitive. So the moisture control, long-term power agreement, gas recycle design, these are very important factors for remedies, and you have correctly found the cost of electricity is most sensitive to the profitability of the entire project. This is really a very interesting topic. I thank you again, and I hand over the mic to Mr. Shen.
Hello, yeah, thank you, Sujit. Excellent presentation.
Thank you.
And you know, like I know he's pretty busy. He's in the implementation of this hydrogen train in USA that he was telling me it may not be possible because of our steel tech thing. He agreed to have this presentation, and thank you very much. And today is, I think, Professor Das is also here. You know, the one what you gave us for critical analysis, that is with him. He saw it and he is working further on this. And if there is any further question from audience, and it is fine. Otherwise, can I just request you to what is the condition of your implementation of your project, that hydrogen train? If you kindly tell very briefly about it.
Yeah, thank you for listening to me, and thank you for sharing all the interesting facts that we shared together in this wonderful meeting. So basically, as you know, Los Angeles will have the Olympics in 2028. So the whole air infrastructure of California is being upgraded for that. So one of them, or two of them, I'm working on two of those projects. One is the Los Angeles Metro Automatic People Mover, which will move all the passengers from the airport to the venues and the hotels, and it's an automated train, electric train. And the other one is a commuter train, the first commuter train in the world, which will run on hydrogen. Both these projects are being commissioned at this moment because we are almost near the Olympic dates and the FIFA dates. So if you Google Zimu on the internet, you will see that train, and same APM. If you Google LAX, it's called LAX Metro, which will move automatic trains from the airport to the hotels, to the venues, the stadiums. So this requires a lot of electrical engineering, infrastructure, automation. And one of the things that people don't know much about me, that I spent a lot of time in safety, and in India, way back in the 1980s and 1990s before I moved to Europe and then to North America. So safety is a big thing, safety and risk analysis. And the other thing that makes a segue, the safety in steel is a big thing, and safety in ferrochrome, and also safety in nuclear safety. Now, as you know, India has just commissioned its fast breeder reactor in Kalpakam, if you have read the news, and first critical commissioning. And this started when I was studying in IIT Kharagpur in the 1980s. The work started. So it took this much time to establish, and I congratulate the Indian engineers and people and the scientists who have worked on it, and many of them are my friends. So safety is a very critical thing, and so that's what I would like to share about myself and the work we do. So any one of you who would come to the Los Angeles Olympics or who would travel to Canada, to Edmonton, would ride my trains, the trains that I have certified. Thank you.
Great. Thank you.
Pritish, I have a small question to
Mr.
Dr.
Shankar Chaudhary has a question for you.
It was an excellent presentation, Dr. Sengupta. I am Shankar Chaudhary. I presented the previous paper. I have a small suggestions, or maybe this thing, that instead of going for a rotary kiln system, why can't we think of a vertical shaft furnace, which will be much easier? Because, then rotary injection of gas is difficult, because Alice Chalmers, way back, they tried to inject liquid fuel into the thing, and one of our sponge iron plant in India, that is OSIL, utilized that. But ultimately, it was not a very success. So if it is a vertical furnace, like, all the gas-based sponge iron plant are vertical, if you think in the vertical furnace, because you are using pellets, so no problem, and oxygen is a gas, so I think the gas-solid reaction will be also very good, and at the same time, the reduction percentage will be better in a vertical shaft furnace.
Very good point, very good point. Your presentation also was very good, very interesting. And we had a lot of learnings from your presentation too. Yes, we can evaluate it, but what we did is why we went for rotary, and because of my previous work in Air Liquide in France, so they had a pilot scale rotary furnace, pretty proven, well run. So that's why for the pilot, we said that maybe rotary kiln is the best from our research and development, but we can certainly look at a vertical furnace. And the other thing, I also worked when I was in India on the roll melt process. As you know, the roll melt process was a very innovative process towards steel making, which eliminated the coke ovens and all that stuff. So that is also a rotary, sort of rotary fluidized-based furnace. So that's how I was attracted to the rotary and the fluidized beds. But certainly we can look at a vertical furnace too and do the design and changes and see whether it can offer the same benefits or not. Certainly a good idea.
Thank you. Thank you very much.
Yeah, thank you. Is there any other question from audience? Yeah, Siddhartha, do you have anything? Okay. Thank you, Sujit, for the excellent presentation. Sorry to keep you where he woke up at 2 o'clock night there. We and Sujit, actually, I can tell him because we studied together and we are in the same hostel. Yes, sir. Thank you, Sujit. Thank you very much.
Yeah, very nice.
A lot of big round of applause for you. Thank you. Thank you very much.
Thank you.
Yeah.
Thank you.
Now may I request,
have a good day.
Yeah, thank you, Sujit. We are missing you in person here, but however, your gift, what Rajiv will be giving to others, it will be kept for you whenever you come here.
Thank you very much. Have a good day, have a safe day.
Thank you so much, thank you. Now can I request Rajiv to, and also the presenter, Vibhor and Shankarda is already there, and Sarosh. Yeah. Please request you to come to the stage. From Steel Decarbonization to all our presenters. And next one, I think like we should get prepared for the valedictory very short. What is the valedictory? Now you go for a